Good afternoon, everybody. My name is Tony Cohn. I'm at the University of Leeds, and I'm chairing today's BCS Awards lectures for the Lovelace Medal. So welcome, everybody, and thank you for attending this year's virtual event. Although I'm sorry we can't hold this event in person, I'm very pleased to say this virtual format means we again have a very high number of registrations. I want to start by saying a few words about the background to this event. The Lovelace Medal was established by the BCS in 1998. The medal is presented to individuals who made a contribution which is of major significance to the advancement of information systems, or which adds significantly to the understanding of information systems. It is given in memory and honour of the great Ada Lovelace, mathematician and scientist who worked with and was an inspiration to the computer pioneer Charles Babbage. Over the years, through the medal, we have celebrated the contribution of many great people, including Karen Spark-Jones, Tim Berners-Lee, and Linus Torvalds, to name just three. In 2020, the BCS announced two winners of the Lovelace Medal, one of which is a joint award. The recipients are Professor Ian Hollicks of the University of Oxford and Professors Nick Jennings of Loughborough University and Mike Waldridge of the University of Oxford. Today, we will virtually present the medals to the winners and have an opportunity to listen to the lectures given by them. I would now like to virtually present the first of these medals, Professor Ian Hollicks, for his work in the field of knowledge representation and reasoning. Very many congratulations to Ian. I don't have a medal I can give you over the screen here, but I'm assured that the medal is in the post. So I would now like to introduce and invite Professor Udi Sattler from the University of Manchester to introduce Professor Horrocks.
Thank you very much, Tony, and a very warm welcome from Manchester. I hope you're all sitting comfortably and you are ready to enjoy Ian's lecture. I am extremely pleased to be able to introduce Ian, and I want to share with you why he is such a wonderful recipient of the 2020 Lovelace Medal. First, I want to talk about his research contributions. Over the last, drumroll, 26 years, he has made an impressive number of these contributions, and they range all the way from theory, including computational complexity and undecidability results, via the design, implementation and optimization of sophisticated reasoning techniques and algorithms to their use in real applications. And they include spin-outs such as the current Oxford semantic technologies. In particular, he has designed the description logics underlying OWL and various reasoning techniques for these logics, using a wide range of reasoning techniques, from tableau-based and hyper-tableau-based ones via consequence-based algorithms to over and under approximation-based ones and those based on materialization. And he has done this for the usual reasoning tasks, as well as for query answering and explanation and updating, etc. And he has co-developed not just one or two leading state-of-the-art powerful reasoning systems, but to my count, at least 6 major such systems. They include FACT, Pyramid, ELK, Sequoia, Pagoda, and RDFox. So that's super impressive. And all these systems are based on calculi and optimizations that are not just only extremely well engineered, but also thoroughly analyzed and proven to be correct. That is, sound complete and terminating and doing exactly the right thing and never lying. So Ian has absolutely shaped and led the field of automated reasoning for description logics and related formalism from theory through to practice. A lot of his work was super brave. Just one example, he designed and implemented decision procedures for logics that were known to be X-time hard and therefore unimplementable and totally impracticable, according to world-leading experts. But Ian threw their advice to the wind and developed FACT anyway, and it turns out, thanks to his clever optimizations, that FACT worked very well in practice. So that was super brave and extremely successful and shaped the field in massive ways. And Ian didn't stop there. equally importantly, he has put in a lot of hard work to get these systems being useful and being used in practice. For example, he has been a leading force in various standardization committees and shaped the development of semantic web ontology languages, namely OIL, DAML+, OIL, and OWL. And this was not a walk in the park. It involved endless hours of hard committee work and heaps of energies and mountains of patience. So he worked on exciting research with a lot of energy, and he somehow still finds time to seek further thrills outside his research. He's a formidable climber, mountain biker, and skier, and never afraid of trailblazing or a hard slog. And finally, and perhaps most importantly, I would like to talk about Ian as a friend, colleague, and mentor. He's great company with a really dry, cool sense of humor, and he's very much a team player. The above mentioned research contributions would not have been possible without his impressive research group. Over many, many years, he built and grew his knowledge representation and reasoning group with great patience, understanding, emotional intelligence, and of course, energy. Having worked with Ian in the past, I know from first-hand experience that working with Ian is a great pleasure and that he brings the best out of students and colleagues alike. And I'm sure that other members of his group, in particular Professors Boris and Bernardo, would agree totally with me on this. So I hope I managed to explain a little bit why Ian is a most deserving recipient of the Lovelace Medal. Like Lovelace, he has done pioneering work in algorithm design, and in Ian's case, also pioneering work in algorithm analysis, optimization, and usage. And also like Lovelace, he has a vision for the application of these algorithms that goes well beyond what other people at this time considered possible, plus a drive to realize these applications. So I want to hand over to the man himself. Ian, please do one of the many things you do best and give us a tour around your research.
Thank you, Uli. So you should be able to see a Q&A button, I'm talking to the audience now, at the bottom of your screen. And I encourage you to type your questions in there, and I'll read out a selection at the end of the talk. So now I'd like to invite Ian from the University of Oxford to present the first of the two talks tonight as part of our 2021 BCS Lovelace Lecture. Thank you.
Firstly, I would like to say how very honoured I am to give this BCS Lovelace Award lecture and to thank the BCS and the Awards Committee. I would also like to thank all the people that I've worked with over the years, in particular, the past and present members of the Data and Knowledge Group at the University of Oxford, without whom none of this would have been possible. In this talk, I'm going to discuss the development of modern knowledge representation and reasoning systems and their genesis in foundational research. I'll start with a very brief review of the historical context. The study of knowledge representation and reasoning, or KRR for short, obviously has a very long and distinguished history. But as time is short, I'll fast forward to early investigations of KRR in the context of artificial intelligence. These include Newell and Simon's General Problem Solver, GPS, which can be seen as an early example of a KRR system. The goal of GPS was to solve arbitrary problems by encoding the structure of the problem as a set of logical statements or rules, and using a reasoner to search for a solution. This line of research led to the development of expert systems. These systems use similar ideas to simulate human decision-making in relatively narrowly defined fields of expertise. The mycin system, for example, was developed to identify bacteria causing severe infections, such as meningitis, and to recommend appropriate antibiotics. The architecture of expert systems already includes the basic features of modern-day KRR systems. There's a knowledge base that represents the knowledge as a set of rules and facts, and an inference engine that answers user queries over the knowledge base. Importantly, the use of an inference engine means that query answers can include not only combinations of the given facts and rules, but also facts and rules that are only implicitly entailed by the knowledge base. Expert systems achieved some significant successes, and they influenced the development of products such as business application suites, but they failed to live up to the overambitious claims that had been made for them. Problems with expert systems included the difficulty of capturing and formalizing knowledge and the intractability or even undecidability of reasoning for many logics. For example, reasoning in propositional logic is already NP complete, while reasoning in first-order logic is undecidable. I'll return to the subject of knowledge capture later in the talk, but for now I'll focus on reasoning. Different approaches to tackling the tractability problem were investigated. The so-called scruffy approach continued to work with very expressive representation languages, often without formalized semantics, and developed ad hoc approaches to reasoning that were probably sound, but invariably incomplete. That is, a yes answer is always correct, but a no answer really means don't know. In contrast, the so-called neat approach used languages with formalized, usually logic-based semantics, restricting the expressive power so as to achieve tractability for sound and complete reasoning. The scruffy approach largely failed. Problems with this approach include the fact that without any formal algorithms or specifications, it was impossible to fully understand system behavior or to rely on consistent behavior across different systems. It was also difficult to understand the degree of incompleteness, which typically wasn't evenly distributed, but rather led to unpredictable pathological failures. Moreover, incompleteness can easily turn into unsoundness in downstream applications. For example, if a diet and health application uses a KRR system to answer queries about allergens, then incomplete reasoning could result in the application incorrectly recommending a given dish as safe to eat, even though it contains dangerous allergens. The field of description logics, or DLs as they're known, grew out of the neat approach. DLs are a family of logic-based KR languages. They're usually decidable subsets of first-order logic and usually restricted to unary and binary predicates called concepts, or sometimes classes, and roles, or sometimes properties. DLs are modular. There are a range of different constructors for building complex formulae, and a given DL is defined by the set of operators supported. The strange-looking names of many DLs are simply acronyms that list the relevant sets of operators. For example, an ontology of human anatomy might include a statement that the heart is a muscular organ that is part of the circulatory system, which can be formalized in a description logic axiom as shown here. The restricted use of quantification allows for a variable-free syntax, but the description logic axiom can trivially be transformed into an equivalent first-order logic sentence as shown below. A major advantage of this logic-based approach to knowledge representation is that answering questions over the represented knowledge simply amounts to logical entailment reasoning. For example, if the ontology additionally includes axioms stating that vascular disease is a kind of disease that affects part of the circulatory system, and that heart disease is a kind of disease that affects the heart, then asking if heart disease is a kind of vascular disease amounts to asking if the corresponding axiom is entailed by the ontology. This means that we can exploit well-understood reasoning algorithms to implement question answering in KRR systems. DL researchers have mapped out the decidability and complexity landscape for various combinations of constructors. There's even an online description logic complexity navigator that will return the relevant complexity result for a chosen set of operators. In addition, DL researchers have developed highly optimized implementations for various languages that seem to offer a good compromise between expressive power and tractability. The work of Franz Baader was particularly influential in the development of DLs. Franz developed model construction algorithms known as Tableau algorithms for several DLs, and he demonstrated with the CRIS system that suitably optimized implementations of these algorithms could be effective in practice. Inspired by Franz's work, Uli Sattler and I extended Tableau algorithms to deal with more expressive DLs. Highly optimized implementations were used in the FACT system, which worked well in several applications, notwithstanding the at least exponential time complexity of the relevant logics. Several other DL systems were developed along the same lines, including Racer, Pellet, FACT++, and Hermit. DL knowledge bases are often divided into a so-called A box, containing ground facts such as Socrates is a man and Socrates was born in Greece, and a so-called T box containing schema-level axioms, often asserting concept inclusions such as all men are mortal. Nowadays, the T box is usually called an ontology. DL applications often focused on T-box reasoning and in particular on supporting the development of large-scale ontologies. They were particularly successful and widely used in medicine and life sciences. For example, DL T-box reasoning is used in the development and maintenance of SNOMED CT, a large medical terminology ontology that is used in the healthcare systems of more than 80 countries, including the UK. A potential killer application for KR emerged with the development of the web and the subsequent idea, promoted by Tim Berners-Lee and others, to make web-accessible data be machine-readable, potentially leading to the development of a massive distributed knowledge base. As a first step towards realizing this ambitious goal, the W3C started work on suitable KR languages. The results were RDF, a language that uses a graphical data model to represent basic facts, much like a DLA box, and OWL, an ontology language that extends RDF with rule-like statements that can be used to define a conceptual model, much like a DLT box. They also developed Sparkle, a query language that is similar to SQL with adaptations to suit RDF's graphical data model. It was decided to base OWL on a description logic, partly to provide clear semantics and partly because of the availability of several successful DL reasoners. The growth of the web and the development of semantic web standards led to an increasing focus on large-scale graph-structured knowledge bases, with perhaps the most prominent example being the Google Knowledge Graph. This uses a proprietary knowledge representation language, but the basic idea mimics RDF and OWL. Another example is Wikidata, which, like the Google Knowledge Graph, covers general knowledge and provides a common source of open data for Wikimedia projects such as Wikipedia. The prominence of knowledge graphs and applications has resulted in RDF and OWL knowledge bases now being often referred to as knowledge graphs. It will be interesting to take a closer look at knowledge graphs, and here is a small fragment of such a graph extracted from Wikidata. The graph is stored as a set of RDF triples, each of which represents a single labeled edge in the graph. For example, this triple represents the edge connecting London to UK via a capital O edge. In RDF, London is called the subject of the triple, capital O is the predicate of the triple, and UK is the object of the triple. As we've already seen, we can equivalently represent these triples as description logic, facts, and axioms. It's also interesting to note that we could store this information in a roughly equivalent way in a relational database, for example, using tables like these. However, the graph form has significant advantages. In the first place, the graph is more intuitive. The knowledge isn't split across multiple tables, and we don't need to understand hidden details of the database schema, such as foreign key constraints, in order to understand the structure of the data and to navigate around it. In the second place, the schema, or at least the taxonomic backbone of the schema, is explicitly represented in the graph in exactly the same way as the data. We can see, for example, that the upper part of this graph, outlined in blue here, defines the schema and is equivalent to a DLT box, or equivalently an OWL ontology, while the lower part, outlined in red, is equivalent to DLA box assertions, or basic RDF triples. Another thing to notice is that each entity occurs only once in the graph and can be arbitrarily connected to other entities. In contrast, in the tabular version of the data, the same strings occur multiple times, and string matching is used in order to make connections in the data. In fact, in RDF, graph entities and edge labels are uniquely identified by URIs. This has the advantage that we can directly refer to entities in other knowledge graphs and access additional information via the web. For example, we can use the Wikidata URI for architectural structure and could use that to access a wealth of additional information about architectural structures. Another feature of the graph data model is that it is very flexible and extensible. For example, if we decide to add information about architects, all that's required is to add the relevant additional triples to the graph. There's no need to change table structures, and we can add arbitrarily many architects. Similarly, if the data changes, then we can delete edges from the graph just by deleting the relevant triple. And the eagle-eyed amongst you may already have noticed that we need to delete at least one triple from this graph. Another very important feature of knowledge graphs is that we can augment the basic schema information that is stored directly in the graph with a rule or ontology language such as Datalog or OWL. For example, we could add a Datalog rule, or equivalently an OWL axiom, which states that things located in the capital of a country are also located in the country itself. This allows us to infer that the Shard is located in the UK and the Eiffel Tower is located in France. This kind of reasoning is critical to support the development and maintenance of large-scale knowledge graphs, allowing for large parts of the graph to be only implicitly represented and automatically updated when the explicitly represented facts change. For example, if we used an additional rule to infer that the Eiffel Tower and Shard are both located in the EU, then we can infer that this no longer holds for the Shard after the deletion of the edge representing the UK's membership of the EU. Finally, in addition to standard retrieval queries, the graphical data model facilitates a range of other query types, including navigational queries and queries that explore structural similarities, localities, etc. The increasing availability and importance of large RDF graphs led to an increasing prominence of data-centric applications. That is, applications where the main focus is on Sparkle query answering over large RDF graphs, augmented with ontologies and/or rules. Most existing DL reasoners were not well suited to this task. Their main focus was on ontology classification reasoning, i.e. computing the class hierarchy induced by explicit and implied subclass relationships. They typically supported the full OWL language, which, as we've already seen, is equivalent to the Sroik description logic. This logic is known to have very high worst-case complexity, specifically double non-deterministic exponential time. This holds for all standard reasoning problems, such as class subsumption, with conjunctive query answering being at least as hard. In fact, the decidability of conjunctive query answering in Sroik is still an open problem. As I already mentioned, in spite of this discouraging complexity result, highly optimized implementations of Tableau and hypertableau algorithms had proved to be very effective for ontology classification, even when the ontology contained many thousands of classes and axioms. However, in data-centric applications, the graph could contain not thousands, but millions or even billions of individuals and facts. Moreover, the algorithms used in existing reasoners can only check candidate answer tuples one at a time, and the number of such candidates is polynomial in the number of entities in the graph. As a result, Tableau and hypertableau-based AL reasoners weren't effective in typical data-centric applications. In order to address this issue, the 2012 revision of OWL, known as OWL 2, introduced so-called profiles. These are subsets of OWL that correspond to smaller description logics that have better computational properties and are more suited to data-centric applications. 3 profiles were defined: OWL2EL, which is based on the EL family of description logics and has polynomial time worst-case complexity; OWL2QL, which is based on the DL-Lite family of description logics and has AC0 worst-case complexity; and OWL2RL, which is based on the datalog subset of OWL, also known as description logic programs, which also has polynomial time worst-case complexity. Like other DLs, as well as complexity results, description logic researchers have also developed effective algorithms for each of these logics, and in the case of QL and RL, these algorithms were particularly focused on query answering. In the case of OWL-QL, the language is designed so that it is possible to use the ontology axioms to rewrite a given query Q into an expanded query Q prime, such that answering the expanded query over the data alone gives the same answer as answering the original query with respect to the data plus the ontology. This has the advantage that data can even be left in legacy stores such as relational databases, with a set of mappings being used to specify how each of the ontology classes and properties is stored in the database. For example, if we consider our example knowledge graph and a query asking for all instances of architectural structures, then we can use the ontology, and in particular the subclass axioms represented in the upper part of the graph, to rewrite the query so that it also includes instances of towers and buildings. This can be seen as a form of backwards chaining reasoning. Moreover, if we additionally have mappings stating that architectural structures, towers, and buildings can be retrieved from the name columns of the respective tables, then we can transform this into an SQL query over data stored in a relational database. In this case, we can equivalently think of the mappings as specifying how the relational data can be transformed into a graph, or in other words, as defining a virtual graph. This is obviously very convenient in cases where we would like to leave the data in relational stores. However, query rewriting only works for very weak ontology languages. For example, it wouldn't be possible to rewrite arbitrary queries if the ontology contained the recursive axiom about location, as this could lead to an unbounded rewriting. In addition, large ontologies can lead to extremely large queries, which can be problematical for typical database systems. In the case of OWL-RL, we can treat the graph and ontology as sets of data log facts and rules, or equivalently as a Horn fragment of first-order logic. We can then exploit data log reasoning for query answering. In particular, we can use a forward chaining algorithm known as the chase, which exhaustively applies the rules until all consequences are materialized in the graph as implied edges. This procedure is guaranteed to terminate as OWL and data log can only entail new edges and not new nodes. Note that we can also think of this as a rewriting procedure. However, instead of using backwards chaining to rewrite the query, we use forward chaining to rewrite the data. If we consider our running example knowledge graph and query, then exhaustively applying data log rules corresponding to the inclusion axioms would add type edges from Eiffel Tower and shard to architectural structure. We can now answer the query directly over the graph, or equivalently over the set of data log facts corresponding to the graph, with the answer being just those individuals that are explicitly stated to be instances of architectural structure. As we have already seen, we can use the same procedure to materialize our location rule. We could then answer a query asking for, say, architectural structures located in France and get the Eiffel Tower as an answer. Materialization has the advantage that query answering can be very fast, as only the materialized facts need to be considered. Materialization can be treated as a pre-processing step, the cost of which is amortized over subsequent queries. However, materialization should still be as fast as possible. In some existing systems, for example, materialization over even moderately large graphs can take days. We also need to consider what happens if the data changes. For example, if we add a rule stating that things located in a country that is a member of a union is also located in the union, then we would infer that the Eiffel Tower and shard are both located in the EU. Now, when we update the asserted graph by deleting the edge that represents the UK's membership of the EU, the edge representing that the shard is located in the EU is no longer entailed. Ideally, this edge should be automatically removed, a process known as truth maintenance. However, few, if any, existing data log or RDF systems support truth maintenance, or at least correctly support it. In most cases, deleting edges from the graph would require the deletion of all derived edges and a repetition of the full materialization procedure. As I already mentioned, this could be very time-consuming and would make the use of such a system infeasible in a setting where the data is frequently updated. Finally, we can also use materialization, or in fact any OWL query answering procedure, to answer queries in OWL. This is done using a technique called the combined approach. Roughly speaking, this involves over-approximating the EL ontology so that it becomes an RL ontology. In particular, new individuals are introduced and used to scholemize existentials in the EL ontology. We can then answer queries over the graph and RL ontology using, for example, the materialization procedure that we've been looking at. The over-approximation step means that answers are guaranteed to be complete, but may be unsound. That is, they'll contain all answer tuples, but might additionally contain non-answer tuples. However, we can use a subsequent polynomial time filtration procedure to remove any spurious answers, leaving a sound and complete answer. To summarize, OWL seems to offer a good compromise between expressive power and scalability, and using a data log materialization-based approach could in principle allow for very efficient query answering. However, in practice, materialization-based reasoners left much to be desired. In the first place, materialization could be very time-consuming, and even if this can be treated as a pre-processing step, taking hours or even days to perform this step is at least inconvenient and probably impractical in many settings. This problem is exacerbated if the data is frequently updated. These considerations motivated our research into materialization-based reasoning, and our development of the RDF-OX system. Our objective in developing RDF-OX was to support applications where the focus was on SPARQL query answering over large-scale RDF graphs, augmented with L2RL ontologies and/or data log rules. As we've seen, materialization effectively means repeatedly answering queries represented by the bodies of rules and adding the answer triples back into the graph. An RDF graph is just a set of subject, predicate, object triples, and query answering involves computing joins over the triples. To do this efficiently, we need the triples to be accessible in various orders, for example, in subject order or object order. And we also need indices that allow us to rapidly find appropriate entry points into the various orderings. Moreover, we need to update the relevant data structures as new triples are added. These considerations led us to develop novel in-memory data structures for RDF-OX. This obviously limits the size of graph that can be stored in a single server, but careful optimization of the data structures allows for billion triple graphs to be stored even on a relatively modest server, and this is large enough for most realistic applications. Some details of the main triple store data structures are shown here. In an RDF graph, each subject, predicate, and object is a URI. However, for space and efficiency reasons, a dictionary is used to transform these URIs into integers. The triples are stored in a triple table, each entry of which stores the subject, predicate, and object, along with linked list pointers that allow the triples to be accessed in various orders. Several hash-based indices are also maintained so as to allow for duplicate detection and for rapid access to relevant positions in the table. RDF-OX also exploits modern multi-core architectures in order to parallelize materialization. To balance the workload, each thread retrieves a new triple from the triple table, processes it using the rules and any preceding triples, and writes any resulting triples back into the table. This is in fact the well-known semi-naive algorithm. In order for this procedure to be efficiently parallelized, RDF-OX's data structures allow for updating with minimal locking. For example, when inserting a new triple in one of the linked lists, RDF-OX uses a compare and swap instruction to update the relevant link, which avoids any need for locking. Consider, for example, a situation where two threads are adding triples to the table and inserting them into the SP list after the 132 triple at the top of the table. Both threads set the new triple's next pointers to be the same as the next pointer from the 132 triple. They then use a compare and swap instruction to set the 132 triple's next pointer to point to the new triple. Only one of these can succeed. Let's say it's the first thread. The first thread has now completed its insertion operation. The second thread sees that its compare and swap instruction failed, and so it simply repeats the process. This time it succeeds, and both triples have been correctly inserted without having to lock the triple table data structure. An evaluation on some standard benchmark datasets shows that RDF-OX can achieve speedups of up to 20 times on a 16-core machine with 32 threads. This might seem counterintuitive to those who, like me, are not very familiar with processor architecture, but hyperthreading allows for multiple threads to run on a single core, increasing core utilization by swapping between threads when one is stalled, for example, as a result of a cache miss. Finally, RDF-OX implements incremental addition and retraction using a novel extension of the delete rederive algorithm known as DRED. DRED works by first eagerly over-deleting all facts that depend, possibly indirectly, on a deleted fact, and then rederiving all facts that still hold due to some alternative derivation. This has the advantage that it doesn't require any additional data structures, and it can handle arbitrary rules, including recursive rules. However, eager over-deletion and the subsequent rederivation of facts can be very inefficient, particularly when facts participate in long inference chains. In RDF-Ox, deletion is interleaved with checks to determine if facts still hold via alternative derivations, which avoids excessive over-deletion and hence improves the efficiency of incremental materialization. Our first paper on RDF-Ox was published in 2014, and over the next few years there were several successful industry applications of the system. For example, Kaiser Permanente used rules to capture care quality standards and to check that patient data indicated compliance with these standards. However, as researchers, we were unable to provide the support that was needed to go beyond proof of concept applications, and this led us to commercialize RDF-Ox via a spin-out company, Oxford Semantic Technologies, which was established in 2017. However, although RDF-Ox was well engineered, it soon became obvious that there was a huge gap between a research implementation and a viable product. On the one hand, we needed to add some new features to the representation language, and on the other hand, we needed an industry-strength system architecture. Regarding the representation language, one important issue was data types and values. In principle, OWL supports all of the XML schema data types, but this support extends only to allowing types and values to be used in a similar way to classes and individuals. In realistic applications, it is often necessary not only to represent data values, but to manipulate and combine them using built-in operators for subtracting numbers, concatenating strings, accessing the year and a date, and so on. Aggregation functions such as sum and average are also important. None of this is very difficult or interesting from a research point of view, but it requires a considerable amount of engineering effort. Another issue was value invention. As I already mentioned, OWL-RL and vanilla datalog don't allow for adding new nodes to the graph. However, it's often very convenient to use rules to compute new values and store them in the graph. For example, in a recipe application, we might want to use rules to add a calorie value to each recipe by summing the calories of the ingredients. This is a little more complex as we need to ensure that materialization doesn't add an unbounded number of nodes to the graph. However, this has already been studied and suitable solutions can be found in the literature, but implementation again requires significant engineering effort. Finally, OWL and datalog allow us to derive new information, but they don't allow us to check constraints on existing information. This is a well-known limitation of first-order logic. For example, going back to our recipe use case, we might want to compute the calories of a recipe only if the calories are not already explicitly given. This can be achieved by adding negation as failure to the representation language. Again, this has been well studied in the literature, for example, in non-monotonic logic, but again requires significant implementation effort. Regarding the system architecture, RDF-Ox's original system architecture was very basic and consisted of little more than the core reasoning engine, a command line interface, and a Sparkle API. We had to add numerous components, including connectors for external legacy data sources, a persistence layer that allows the graph to be stored and reloaded from disk, a web console for system operation and administration, an extended range of APIs to support applications and third-party extensions, and adaptations to allow for running the system in environments ranging from edge and mobile devices through to the cloud. Finally, we had to add all the usual enterprise features such as access control and transactions. All of this engineering effort to develop RDF-Ox into the fully fledged system that we have today has taken several years. However, we're now able to support large-scale and mission-critical applications. For example, RDF-Ox is being used by Festo, a German multinational producing control and drive technology for factory and process automation. Festo uses RDF-Ox to support the design of production line systems, including checking compatibility between the numerous components involved in such systems. The knowledge base includes a complete specification of their component catalog, along with rules that capture expert knowledge about compatibility between components. For example, a rule might capture the knowledge that a motor is compatible with a power supply only if the power supply is of the appropriate voltage and provides at least as much current as is required by the motor. I'm sure that, like me, many of you have been struck by the fact that, as is often the case in computer science, we seem to have come full circle, and what we have in this application sounds very much like an expert system. So, even if the early claims for such systems were a bit optimistic, we did eventually figure out how to make it work. However, I should mention that KRR in general, and RDF-Ox in particular, is also being used in a wide range of other applications, including data integration and analysis, complex pattern detection, personalization and recommendation, and semantic search and browse. Well, it's about time to wrap up, and I would like to finish by reviewing some of the barriers and milestones encountered during the development of knowledge representation and reasoning. As we've seen, one of the main barriers has been scalability. This is a problem that can never be completely solved, as reasoning is inherently intractable in many logics. However, it's now much better understood, and we've been able to identify logics that combine useful expressive power with good computational behavior. Moreover, we now know a great deal about algorithms, implementation, and optimization techniques, not to mention improvements in hardware. As a result, we're able to build systems like RDF-Ox that are based on formally specified and provably correct algorithms and can provide effective reasoning support for large-scale applications. I should also say something about acceptance. This was a problem for a long time, partly due to the bad reputation for scalability, which was a long-standing legacy of early AI systems, and partly due to the confusing range of different KRR languages and systems. The standardization of RDF, OWL, and Sparkle helped to address this issue by establishing a common language framework and also by encouraging people to take a look at modern KRR systems and to discover that they'd come a long way since the early days of AI. Standardization also encouraged the development of tools and infrastructure and was critical to wider acceptance by industry and the evolution of research systems into viable products. As far as knowledge capture is concerned, which I did promise to come back to, I don't have time to say very much about that, but it has also been the subject of a huge amount of research and has been revolutionized by developments in digitization, the web, crowdsourcing, natural language processing, and sub-symbolic AI. For example, much of the knowledge needed for applications like the Festo one, including product catalogs and the like, already exists in digital form. Extraction of knowledge from the web is also a very active area of research, and combinations of natural language processing, machine learning, and reasoning are being used to automate or semi-automate the construction and curation of knowledge graphs. Looking to the future, a deeper integration of symbolic and sub-symbolic AI clearly has tremendous potential and is one of the hottest topics in AI research. Finally, I want to thank again all of the people that I've been lucky enough to work with over the years. I already name-checked Franz Bader and Uli Sattler, And I'd also like to mention Boris Motik, who is the brains behind both the design and implementation of RDF-Ox. All that now remains is to say thank you for listening, and I'll be happy to answer any questions. Can everyone hear me? Can you hear me, Tony?
Yes, I can hear you fine. Yeah, we can see you as well.
Good. Okay. Thanks for the question. Yeah, well, obviously systems like the ones I've been describing don't actually are not able directly to deal with uncertain information. But one of the things that systems like RDF-Ox can do is that you can insert facts or rules that would lead to the derivation of some kind of contradiction. And you could, you can either do that by deriving explicitly false, or even introducing your own sort of designed predicate to mean that, that there's some contradictory information in there. But the materialization is still there for you to query, so you can ask queries over the materialization and you'll get back answers, even if there's some contradictions in the information you have. And then it's kind of, buyer beware. You'll get some answers back. One of the things in a logical theory that has a contradiction is actually, in principle, everything is entailed. So, your answers may be good, but they may not be so good, but you still have access to them. You can continue using them, and you could retract or change the information so that the contradiction goes away. And the way RDF-Ox works anyway is that its truth maintenance would bring everything back into good order, and you can carry on from there.
Thanks, Ian. We have a second question from an anonymous attendee who says RDF-Ox seems to be returned back to implementing RDMS types machinery, but for RDF. I guess that's a statement. Perhaps you'd like to comment on it.
To some extent, that's true. The design, but we're talking about data log here, and data log is just a fragment of first order logic, the same as all of the description, or pretty much all of the description logics are just fragments of first order logic. Actually, the design of the OWL-RL language was explicitly informed by this idea that, well, maybe we'll define one fragment, OWL-RL, which is actually just the sort of overlap between the data log style fragments and the description logic style fragments. So that's actually the definition of OWL-RL. That actually restricts data log a little bit, because you can, in this fragment, are only rules that have a kind of tree-like structure that are consistent with the description logic part of the language. And it's true that in RDF-Ox, we actually decided, well, you know what, actually, as we're supporting more or less a subset of data log, we might as well just support the whole of data log. So to some extent, it owes a bit more to the database side of things than the description logic side of things.
Thank you, Ian. Perhaps I could just ask you a question. At the end of your talk, you talked a little bit about the role of machine learning, particularly in the knowledge acquisition problem, which of course is critically important there. I was wondering whether you saw a place for machine learning in actually improving the efficiency of the reasoning process itself. I know there's been some work done, for example, by Alan Bundy and others on that.
Yeah, quite a few people actually have looked at this idea. I haven't personally seen anything that I would say looks terribly encouraging from that point of view. If you want the same sorts of features that you want to have in an application, say like the Festo one that I was describing, where you really need to be 100% confident in the answers that you're getting. You're about to install a kind of $10 million production line equipment in some customer's factory, and you don't want a sort of 95% likelihood that it's going to work when it gets there. You really want crisp reasoning that gives you a sort of 100% confidence that it's going to work. I mean, but these kinds of more machine learning oriented query answering systems might be appropriate in other kinds of applications where you don't worry so much about absolute correctness of the answers, but you also like some of the features that those systems give you, which is perhaps being able to come up with an answer when, from a logical point of view, you don't have sufficient information. So horses for courses, I would say.
Okay, thanks, Ian. We're kind of pretty much out of time, but we've got one last question, which we'll try to squeeze in if we can answer it quickly. What's the merit, or is it possible to use ontology-based knowledge base in a machine learning and deep learning for learning and automation purposes? Can it leave us?
Yeah, I mean, I don't have time to say much about that, but there are a huge number of different ways. I mean, one thing I could point you to is zero-shot learning, for example, where you try to, be able to recognize objects that weren't seen in the training data, and you can do that by using an ontology in conjunction with the learned model to try to understand the relationships between the unseen things and the things that you saw in the training data. But that's just one example off the top of my head. There are many, many examples to try to make AI be more explainable.
Okay, thanks, Ian. So I'm afraid we're out of time now, but thanks again. But in fact, I'm going to invite Professor Thomas Eiter from TU Wien to give the formal vote of thanks to our speaker tonight. Over to you, Thomas.
Can you hear me?
I can, yes.
Okay, so welcome from Vienna. Greetings from Vienna. Thank you very much. Well, it's a great pleasure for me to give this vote of thanks to Ian. So thank you very much for this excellent talk and this lecture, which was very inspiring, I have to say. And I mean, it has already been said that Ian is really a pioneer in these fields, in knowledge representation and reasoning and in semantic web. And he made many important results, both on the theoretical and the practical side. And actually, the talk was not always highlighting what his achievements were, but I just want to stress this: the fact system that he built was a real landmark in 1998, which was just recently, last year, honored as an influential work by the Principles of Knowledge Representation and Reasoning Conference as a classic paper. And it provided novel theoretical results to make tableau-based reasoning performing. And he also showed very excellent practical skills to implement such a system and to achieve performance for large ontologies. This actually was a game changer for description logics and opened the door for numerous applications of description logics. And he then worked, as we heard, already on extensions of logics optimizations and implementations from fact, and was creating description logics like Schick and Strike. I mean, the names, as we heard, are a bit funny, and you could think of, if there are children in the room, they might ask, is Shrek also description logic? Is Shrek a friend of Schick and Strike? Well, never mind. No? And as we heard, there were the standardization efforts at the World Wide Web Consortium for description logics and for a web ontology language. And they're really key to a semantic markup of the web so that the web really can be made usable. And Ian was a driving force and to some extent also a mastermind behind OWL, and in particular behind the OWL 2 standard. So it is the second version, because the first was released in 2004 and the second in 2009. And Ian was there chairing actually the committee that was just driving the development of that standard. And Strike, now our friend Strike served as the basis. And well, we heard about OWL-RL already. Well, one can see it as a fragment of Strike to have a tractable profile for reasoning, for efficient reasoning. And it was the personal commitment and the vision and also the endurance of Ian, which made this in the end possible. I'm very much convinced on this. This had a huge impact and actually put description logics as the most important area of knowledge representation and reasoning in the spotlight. And more tools for ontology design then became also available. SNOMED was mentioned at some point. SNOMED is a good example of that. It is widely used around the world. Ian was mentioning more than 80 countries. It was informal at the beginning, but it obtained a formal semantics and also tools for really doing the development and the maintenance of this ontology. How important such role and vision is that Ian has was, or I could experience myself in 2005 at the workshop at the World Wide Web conference in Edinburgh, where Ian was invited at this workshop to comment on the possible development of standardization of rules for the web, which later became the RIF standard. And it was very insightful of him to say this is a too complicated story. He showed a slide with a plane that had all bells and whistles and all kind of passengers on top of it. And he said, this will never really fly. And to some extent, he was really right about this. So Ian serves as a role model for such efforts. And actually just last week at another workshop, I mean, Ian was not invited and maybe could not come because of the pandemic. It was, one was talking about standardization, for example, stream reasoning. We heard also that Ian has been developing many further systems apart from FACT. And ELK, for example, it was mentioned, is still used by SNOMED. Ian made many other contributions, so I have not the time to mention all of them, but it's noticeable that he branched out from ontologies to rules, specifically to data log and extensions, and he's at the front of research there as well. And we heard about RDFOX quite a bit that he developed with Boris Motik, which is a really highly scalable and commercially exploited data log solver in the web context. And it really is very innovative. For example, in 2017, their data log extension with arithmetic earned the Best Paper Award. So this is a significant achievement. It's also satisfying for me personally to some extent, because I remember that Ian was at the beginning a bit skeptical about data log and its potential. So it's very satisfactory to see that he actually turned to that subject as well now and is one of the driving and leading researchers in that area as well. So let me just conclude that Ian is really a pioneer and a worldwide leader in his areas in knowledge representation and reasoning, but also in semantic web, and is highly recognized in the community. For example, as editor-in-chief of the Journal of Web Semantics, or as the president of the Semantic Web Science Association. He made many important and for sure lasting contributions, and is really a role model for others in the field. And his work combines theoretical results with clever and smart engineering to make the sheer impossible then to become possible in the end. So I'm really think that Ian highly deserves highest recognitions for his groundbreaking work. And so I'm particularly happy to see that the other Lovelace Medal is awarded to him. So cordial congratulations, Ian and Ad Majora. Thank you very much.
Thank you, Thomas, very much. And now we move on to the second part of today's event. And I'd like to virtually present the second of our two awards tonight. And that's to the joint winners in this case. It was a joint nomination. And the nominations were for Professor Nick Jennings, now of Loughborough University, and Professor Mike Waldridge of Oxford University for their work in the field of multi-agent systems. So very many congratulations, Nick and Mike. And again, I can confirm that the medal is in the post. But I'd like now to invite Professor Michael Luck, King's College London, to introduce our second pair of joint winners. Thank you, Michael.
Thank you, Tony. Let me say that I am genuinely delighted to have been asked to introduce Professor Nick Jennings and Professor Mike Waldridge, both of whom I have known for over 25 years. But I will say that it's an impossible task. There's simply too much to say. Individually, Nick Jennings and Mike Waldridge are outstanding computer scientists, and one might argue that each merits winning this award alone. but together they have been phenomenal. In particular, as two of the key founders of the field of multi-agent systems back in the late 1980s and early 1990s, their work has been instrumental in transforming it from a niche sub-area to becoming a standard part of contemporary computer science with a global research community. The vision of multi-agent systems that they espoused is that the world is not composed of individual agents that act in silos, but instead that interact to achieve individual and collective goals. These systems cooperate, coordinate, and negotiate with each other to do things that they could not do alone or not do as efficiently, perhaps like Mike and Nick together, although I suspect they probably could do it alone. Their work has laid the foundation for a conceptual underpinning for multi-agent systems, and their knowledge engineering review paper is not only the most cited paper in the area, but it also received a special recognition award from the International Foundation for Autonomous Agents and Multi-Agent Systems. But their joint and individual work has also paved the way in several other areas, including agent-oriented software engineering, theories of cooperation, coordination, and negotiation, computational economics, and various applications, including disaster response, smart grids, and citizen science. Nick is 1 week into his new role as Vice Chancellor and President of Loughborough University, having previously been Provost for Research and Enterprise and Professor of Artificial Intelligence at Imperial College London. He was the inaugural Chief Scientific Advisor to the UK government on national security, and previously the UK's first Regius Professor of Computer Science at the University of Southampton. He was appointed Companion of the Order of the Bath in the 2016 New Year Honours List for services to computer science and national security science, and he has received numerous awards for his research, including the ACM Autonomous Agents Research Award in 2003 and the Computers and Thought Award in 1999 for contributions to multi-agent systems. Mike is Professor of Computer Science in the Department of Computer Science at the University of Oxford and a Senior Research Fellow at Harvard College, as well as being a Program Director for Artificial Intelligence at the Alan Turing Institute. Until I think a little over a week ago, he was head of the Department of Computer Science at Oxford, where he has been since 2012, and before that, Professor of Computer Science at the University of Liverpool for 12 years, including, I think, a stint there as head of department too. This year, he received a Turing AI World Leading Researcher Fellowship from UKRI, and like Nick, he has received numerous awards for his research, including the ACM Autonomous Agents Research Award in 2006, and this year, the AAAI EWI Outstanding Educator Award. Mike has also written 2 popular science introductions to AI, The Road to Conscious Machines in Penguin's classic Pelican series, and perhaps most iconic to those of a certain generation, The Ladybird Expert Guide to Artificial Intelligence. Both Nick and Mike have been heavily involved in community leadership with numerous conferences, advisory boards, and steering committees chaired, especially in relation to the International Foundation of Autonomous Agents and Multi-Agent Systems, and journals edited. In particular, both have been editors-in-chief at different times of the journal Autonomous Agents and Multi-Agent Systems, as well as being involved in various other editorial boards. Both are ACM Fellows, AAAI Fellows, EurAI Fellows, AISB Fellows, BCS Fellows, and members of Academia Europaea. I could go on, but in the interests of getting to the main event, I won't. Let me just finish with a personal note. I met Nick and Mike both properly at the first International Conference on Multi-Agent Systems in San Francisco in 1995, with many hours, I think, in what was named the Gold Dust Saloon. While I have collaborated with them on different occasions, I have really always been watching and learning from them in different ways, not just in their technical contributions, but also in their approach to research and their approach to people and life. I have turned to both of them for guidance and advice over the years, and they have always been supportive and generous with their time. I continue to be in awe of their rich array of talents and achievements, as again and again I see them do more that is new and better. They have been, and continue to be, servants to their research communities, to their institutions, and to the sector. Ladies and gentlemen, it's my privilege to introduce the 2020 BCS Lovelace Medal winners, Professor Nick Jennings and Professor Mike Waldridge.
Thank you, Michael. So now I'd like to invite Professor Nick Jennings, CB, and Professor Mike Waldridge from Oxford University to give the second of the two talks tonight, comprising the 2021 BCS Lovelace Award Lecture event.
Welcome, everyone. My name's Nick Jennings, and I'm the Vice-Chancellor of Loughborough University.
Hi, my name's Mike Waldridge. I'm Professor at the University of Oxford. And I'd like to say on behalf of both of us how delighted and honoured we are to be recipients of this year's Lovelace Medal. In this first part of the talk, we're just going to say a little bit about how we got involved in multi-agent systems and how the early ideas began to shape the field, which we were both involved in. So the first thing to say is, when multi-agent systems really started to take off in the mid-90s, they emerged from many other ideas that were out there in the community. There was Carl Hewitt's actor model, which Carl proposed as a model of concurrency and has subsequently become very, very widely established and widely used as one of the basic concurrency models. There was the Blackboard architecture, which is basically cooperative problem solving via a shared data structure. Marvin Minsky had proposed the Society of Mind, which was the idea that the mind is a collection of interacting agents. And there was an increasing body of work on cooperative problem solving and cooperative expert systems, where the problem solving metaphor was basically one of cooperation. So there were lots of ideas in the air that started to come together to shape the multi-agent systems field. So where I came in was when I started my PhD in 1989 at UMIST. And as an undergraduate, there's actually on the left there is a snapshot of part of my undergraduate dissertation, where it had occurred to me that the future of artificial intelligence, just as the future of computing, will probably involve distribution and concurrency. And so I sketched out my very, very high level ideas for what that might look like. And I was sufficiently interested that I specifically wanted to do a PhD in distributed AI and went out and looked for one. At that time, there weren't very many options. And what I did in my first year of my PhD is actually implement the idea that I'd had as an undergraduate. And on the right-hand side, there's a snapshot from my very first published paper. That's work that I did in 1990. And it's basically a cooperating expert system. We have a bunch of knowledge bases which are communicating and cooperating with each other to solve problems on behalf of the user.
And from my side, I got into multi-agent systems when I went to work at Queen Mary and Westfield College on my PhD, also in 1989. So I had the pleasure and privilege of working on a European funded project. It was a large project. It was a really big and experimental idea at the time to build cooperating expert systems. And in this project, we had a real interesting mix of people who are interested in the theory of how we could build these systems and in the practice. And as a PhD student, that's really what got me interested in the area and in that mix of how you could take theory into practice and learn from that to refine your theory.
But as we began to be more involved and to develop our ideas about what those components, those cooperating components were, started to change. And an idea began to emerge that these components could be active collaborators for us. And it began to change the way that we thought about software. So the dominant paradigm at the time, object-oriented programming, encourages the idea that software is a service. An object provides a bunch of services through its interface, through its public methods, through which it can be accessed. And the ideas that we've been developing started to change that perspective. We instead of just software as providing a service in the sense of object-oriented programming, we started to think of software as an active participant. So if you use a regular app, even today, like Microsoft Word or PowerPoint or whatever, everything that happens on that app happens because you make it happen. You select a menu item or you press a button, and the software is just the dumb recipient of your instruction. But instead, we started to think about these components, these cooperating components, agents as being active collaborators that would cooperate not just with each other, but with us. And that's where the idea of agents started to emerge. And our ideas in this area were crystallized in the 1995 paper, Intelligent Agents Theory and Practice, where we established what became, I think it's fair to say, the fairly standard idea of agents that persists to the present day. And the idea of an intelligent agent is just, it's an AI system which is working on behalf of a user or an owner. It's acting rationally to accomplish delegated goals. So we're giving it goals, we're giving it things we want it to do, and this agent is acting to accomplish those. And in order to do that, it needs a high degree of autonomy, be able to operate independently of our supervision. It needs to be responsive to its environment. It needs to be reactive. It also needs to be proactive. And finally, it needs to be social. And this led to this idea of software systems as societies of interacting, rational, intelligent software agents. And that's the multi-agent systems paradigm.
And so this paradigm was new to the field. AI had traditionally been very much focused on individual agent skills, so on how an individual agent could plan, how an individual agent could problem solve, reason, and perceive. But multi-agent systems brought on top of that the ability to interact in a flexible and sophisticated manner. So we wanted these individual agents not just to operate in isolation, but we wanted to be able to let them cooperate, coordinate, negotiate, behave together as a society. And that is a really fundamental shift. And from our perspective, it's just the natural way to go. If you can build one agent system, you would build a multi-agent system. Now, I would say that at the time, there were many competing areas of theory. Lots of people thought of lots of different ways to try and describe these sorts of systems. But we could already we were coming to the end of our PhDs and our early academic careers, that game theory was very much becoming the dominant theoretical underpinning for our area. Now, that's when we started our PhD. So where have we got to today? So I would say many parts of our vision in the papers that we articulated and wrote at the beginning of our PhD, many of these things have come to pass. So software agents are really common parlance. They exist routinely now in everyday life. Siri, Alexa, Cortana are all realizations of that dream. So they are autonomous, they are able to interact, they're able to problem solving. But the multi-agent part, so the idea of multiple of these agents interacting with one another. So Siri, my Siri, talking to Mike's Siri, didn't exactly pan out in the way that we expected. And that's still very much to come, I would say, in this area. But this doesn't mean, of course, that multi-agent systems didn't happen. They have come to pass and been used in a wide variety of applications. Because as we've said, most real applications have multiple agents within them. They're distributed in some sense in terms of control and resources. And we now see routine applications of multi-agent systems in areas of automated commerce, connected vehicles, multi-robots in warehouses, carpooling, and many others besides. So we really are seeing the fruits of this paradigm, this way of dealing with software systems, very much coming to the fore.
Okay, so in our individual talks, we're going to talk a little bit more about the research that we've done subsequently, and obviously focusing on the more recent research that we've done. And you'll see how those ideas, those early ideas, still shape the field today. So thank you.
So I've always been interested in how the underlying theory of multi-agent system can be applied in practice and how practice can inform those theories. So there are a range of different types of theories and applications, and I want to talk a bit about a few of those. So most of the work in our area is concerned with a number of agents and typically a small number of humans associated with them. where much of the action has been is in single agents interacting with single users and in multiple agents interacting with a single user. I'm going to talk more in the latter category about multiple agents and multiple humans, but we're going to come to that shortly. Another important dimension is the nature of the interactions that are going to happen within these systems. And the agents can be cooperative, they can need to coordinate, or they can need to compete with one another. And again, there's a variety of theory and applications that fall into that realm. I'm going to talk a bit about the real-world deployments of this technology now. So the first one I want to talk about is some security games work, where there's been some game theory-based models of interaction that have been used or been deployed in order to help rangers in Africa look after wildlife in game reserves, and really trying in particular to identify where there are poaching hotspots. This is a system that's now been rolled out to 800 protected areas in 60 countries. Here what we see is that there's cooperation between the rangers. The rangers are a team who are working together, and then there's obviously competition with the poachers. They're trying to have a game of trying to be found versus of trying to avoid being found. A second type of application that I want to speak about is automated negotiation. Here, for example, Walmart uses a series of negotiating agents for lower value contracts at the moment in their supply chain. So they have very complex supply chains with lots of different actors, and they use negotiating agents in order to set up those sorts of contracts with one another. And what they found is that an agent interacts on Walmart's behalf. It knows its preferences, it knows their preferences and the reserve prices where it's willing to go to, and then it will negotiate with the providers of particular goods and services. And what they found is a decent sort of gain within those systems, so 3 to 7% more profitable outcomes. And here the interaction is a competition between the suppliers. Now, as I said, I want to focus on a less explored area of multi-agent systems, which I'm going to call human-agent partnerships. This is where we have multiple agents interacting with multiple humans, and they're all in this big system together. So here, agents interact with humans and one another in a rich and flexible manner. And the aim here is to make this more effective and powerful for both the humans who are involved in the system and the agents who are involved in the system. So it leads very much to a rise in the humans as well as in the robots. In these sorts of human-agent partnerships, neither the humans nor the agents are always in charge. It's a partnership. Human-AI partnerships is a deliberate use of the word partnership to mean its everyday meaning. So they really work together as a team in order to get things done. So partnership, you want it playing to the strengths of both the humans and the machines, because humans are good at some things, machines are good at others, and by working together well, actually you get the synergies that you're after. In these sorts of systems, you continually establish and sustain collaborative relationships, and you want flexible interactions that support queries, suggestions, back and forth between one another. This requires very much the machines to be much better partners than they are at the moment. We all suffer frustrations when we interact with computers and machines, and they feel very resistant to us interacting with them in a meaningful way. In these sorts of systems, we very much need to be able to change that. Now, this view of human-AI partnerships is not a new view. In fact, it's very much a view that Licklider put forward in the 1960s under the banner of man-machine symbiosis, where you really take the benefits and the strengths of both humans and the machines and you put them together for their own best use. There are a number of decent examples of human-AI partnerships working together. So the first one is in the area of medicine. Medicine is an area of AI that's been explored a lot, and one that I think is really ripe for AI to really come to the fore and make a significant difference to society. Now, a lot of medicine is about looking at images or looking through data and trying to find patterns and trying to make observations. And actually, that's something that AI systems are really very good at. They're used to and powerful in terms of the way that they can explore data and look for patterns that aren't readily visible to humans, particularly time after time after time. And so here what you want to be able to have is the machine, the AI system, to be able to look through the huge volumes of data to find interesting things, and then to highlight these interesting cases, interesting images or interesting data points to a human who's able to use their expertise and know-how in order to interrogate that and to come to a conclusion, to come to a diagnosis as to what's going on within this system. And that interaction is starting to happen. We're starting to see systems develop like that. And what you want to be able to do is to, again, have that real partnership. So if the human makes a suggestion, the machine should be able to query that and sort of say, are you sure? Have you considered these particular points in relation to that interaction? And the other way around. So it's a real partnership. And again, in an empirical study, what Path AI found in this particular study that they ran was that the error rate from a study pathologist just working on their own was about 3.5%. From the AI model just working on its own was just under 3%. But when the pair was put together and worked in the way that I've described, actually the error rate was right down to 0.5%. And this is very interesting. It shows that the sorts of errors that people make are different to the sorts of errors that machines make. And when they interplay with one another, then actually what you're getting is that benefit, best of benefit of both of them. I then want to talk about a human AI partnership system that I've been involved with. This is a project that I ran when I was at the University of Southampton, and it was called ORCID. And so this was about human agent collectives or human AI partnerships. We particularly built this system for a range of different technologies and a range of different applications. I'm going to talk about its applications in disaster response. And so what we have in this system here is when a disaster happens, lots of information from lots of different sources gets generated. So some of that might be from social media, some of that might be from people on the ground, some of that might be from satellite images. And here what we have is a system where all of that mass volume of information is being processed by an AI system to be able to make sense of it. It's producing a heat map of where the key parts of the disaster have happened and where key parts of the rescue need to happen. And then what you have is the human being able to look at that more abstracted view, that processed view, in order to understand where to deploy particular rescue teams and particular resources. So the agent summarizes the information to highlight the damage and the casualties. So here you've got a heat map. You've got an area where there's lots of perceived casualties and cooler areas where there's fewer perceived casualties. The first responders then determine what are the highest priority sites. So they're using their human expertise of responding to disasters. And then the humans and the agents co-create a rescue schedule. So which of these high priority areas are we going to send teams to, in what order, with what particular resources at. And so you've got the humans doing their bit, you've got the agents doing their bit, and then you've got the pair doing their bits together. That sort of real partnership piece. We deployed this system. We built prototypes with a global charity called Rescue Global, and then we deployed it in the aftermath of the Nepal earthquake. In particular, what we deployed it to was to look for Rescue Global wanted to figure out where to to site water filters so that the most of the population could get access to clean water. And we ran our system, our human agent collective system, in parallel to their human-only system. And we identified a number of areas and regions that their human-only system didn't. They were brave enough or fortunate enough from our side to take our advice and to go and put water in those areas. And actually, when they went there, they found that those areas were equally in need of water as the areas that they'd identified. So that was sort of that partnership, identifying areas and identifying individuals to prioritize that would not have been prioritized. And that's saving lives of people. And that sort of, for me, was a real key part of this project and sort of that interplay between the theory and the applications. Having identified key areas where their disaster had happened, what you want to be able to do is to deploy the teams to them. So the teams have a number of resources, some of which might be drones, UAVs, some of this might be teams of individuals with particular medical resources. And so what we wanted to construct was a scheduling aspect where you can work out what teams go where with what resources. And again, this was a cooperative human agent collective endeavor. The machine came up with an initial first pass at it. The humans then interacted with it and changed it and saying, well, actually, I think this one should go in front of this one. There was a bit of dialogue and a bit of back and forth. And then that schedule is co-created. And so here you've got coordination of the UAVs, which UAVs go to which places in what order. You also have teaming of the two coming together. So using their experience, the first responders determined which teams are best suited to what areas. The agents compute a draft schedule to minimize completion time. Agents are very good at those sorts of things, and responders tweak as necessary. And then when the schedule is being enacted, it's monitored by both parties for things that are not going as they thought they would go. So that continual monitoring and then sort of updating. Now, some of the underpinning science of these sorts of things, I want to focus on two key areas. So the areas where we really focused on doing new science, new fundamental theories. First area was in Agile Teaming, so where we're able to construct teams of people and software agents coming together to do something, acting together as a team and then disbanding. And that's very common for these sorts of multi-agent systems. We developed a series of methods based on game theory and coordination technologies that would let coordination happen at scale and under uncertainty and involve both humans and software agents. And there are a good number of papers that we produced identifying that sort of area. The second area of underpinning science was in incentive engineering. Now, in these systems, there's no one entity that owns all of the agents or all of the people. They represent different individuals, different organizations, and different sets of resources. And the way that you work in these systems is not by command and control, it's by incentives. So you offer incentives or you construct reward systems to make sure that the individuals within them, the choices they can make them individually, and they're aligned. And when they all do make their individual choices, actually the collective or global behavior that emerges is what is desirable from a system perspective. So really looking at how you can design systems using mechanisms from game theory and behavioral economics in order to work out what are the best types of incentive to put into these systems. So back to the dreams and reality piece. So that's an example of human agent AI partnerships. I want to end by talking about how these systems are going to be built in the future and what some of the challenges associated with them are. There are a range of challenges that come from dealing and building AI systems. So AI is still far from a solved problem, and there are many complex problems that we need to solve in AI systems. Here I name a few. So coping better with data with a range of properties, sources and characteristics, not homogeneous data, but very heterogeneous data. Constructing systems where we're able to transfer what we've learned from one system or one situation more readily and more easily to another. And also low power approaches and hardware for sustainable operation. A lot of AI systems today use massive amounts of power and crunch huge amounts of data in order to get their results. That's just not sustainable from a going forward perspective. So you have all of those problems that all AI systems face. And then you have some from the fact that you have multiple agent systems. And here some of the key challenges are about making machines much better partners. So machines that are able to take guidance, make suggestions, explain themselves, know when to lead and know when to follow, figuring out how we construct teams and agents that are able to do this is a real scientific challenge, bringing together lots of distinct disciplines in order to do that. The second big challenge is making the system outcomes both more predictable and more efficient. So how can we make sure that the cooperation, that the coordination, that the negotiation I spoke with at the beginning is able to operate effectively to deliver us what we want to be able to do. And thirdly, really ensuring that the partnership piece, so the complementary expertise of the humans and the agents come together in the best possible way to give a rise to both of those. So these are some of the key challenges in the area. And for me, I think sort of the way that AI is going to go and the way it's going to pan out is very much in this future of multi-agent systems. Historically, AI has focused very much on individual technologies, on individual decision makers and individual sub-activities, planning, reasoning, acting. Now, the agent perspective has brought those together into a more holistic perspective so that you're able to construct now, and we're interested in constructing complete entities that are able to sense, decide, and act. And that's a good step forward. But once you've been able to build one of those, you won't stop with wanting to build one, because actually most real problems, most real applications are distributed. There are very few problems where there's just one actor. Most problems involve multiple actors, multiple organizations with their own resources, with their own aims, and with their own objectives. And that naturally leads you into the area of multi-agent systems. So this really is going to be the future, and how we can get those flexible interactions to manage those dependencies is very much where I think AI will be going in the coming years. It's a great honor for me to receive this award, and in particular to receive it with my good friend and colleague, Mike Waldridge. We've worked together for 30 years now. This was us when we started our journey as PhD students in this area. Thank you very much.
Hi. So in this presentation, what I'm going to do is I'm going to talk about some work that I've been doing over the past decade or so, which is about developing techniques to understand equilibrium properties of multi-agent systems. So we're going to start by motivating this, explaining why we're interested in doing this and why I think it's important. And then I'm going to introduce a framework, a general framework that we've been developing called rational verification. And as we'll see, rational verification combines ideas from automated verification and game theory into understanding multi-agent system dynamics. I'm then going to introduce a specific framework called reactive module games, which is a framework that we've implemented and is online that you can play with. And I'll just briefly wrap up with some conclusions and future work. So multi-agent systems, as we've described in the first part of our talk, are around us. They are widely used in the world, and possibly one of the most important, albeit hidden, examples of multi-agent systems in the world is the use of multi-agent systems on the global markets. Most trading on the global markets, whether they're trading stocks or currencies and so on, is actually done by computer programs. They're agents. They're operating very, very quickly on timescales that are far too swift for humans to be able to understand and understand and control. And they're doing it basically outside human control as a consequence. And bitter experience tells us that systems like that have unpredictable dynamics. And the most famous example of this is 6th of May 2010. We were having a general election in the UK, which brought in a coalition government led by David Cameron. But over on the other side of the Atlantic, on the afternoon of 6 May 2010, something very strange happened. In a very, very short period of time, the Dow Jones Industrial Average completely collapsed. For some very short periods of time, some major shares traded for just a penny. Accenture is a famous example of this. You would have had to move very, very quickly because it was a very brief period of time they were trading at that level. And then, weirdly, the markets bounced back. And this is what it looks like. This is the Dow Jones. This graph is the Dow Jones Industrial Average over the afternoon of 6 May 2010. And you can see the market slowly going down, but not dramatically going down. And then it plunges. And you have to understand this is a period of about 15 minutes that it took to plunge, to wipe something like $1 trillion off the global markets. But then it bounced back. You know, that's 15% of the total value of the markets gone in the space of 15 minutes. But then the markets bounce back. So there are many complex reasons for flash crash. I should say this was the first flash crash. There have been others, not as dramatic. But one of the most important is simply that this is a multi-agent system. These are computer programs that are operating autonomously without direct human intervention, and they're operating on tiny timescales. And systems like that are prone to, complex systems like that are prone to unpredictable dynamics. So the ultimate goal of our research, what we really want to do, is to be able to understand and manage these multi-agent system dynamics. And the approach that I'm going to talk about here, and we've used other approaches, is to treat the flash crash as a bug. It's a bug in the system, and what we're going to do is we're going to bring to bear on that bug all the techniques that we've developed throughout computer science to try to identify and resolve bugs. So the particular approach that we use derives from work on model checking, and model checking is probably the most successful automated approach to formal verification and correctness. And the basic idea, the basic insight in model checking, which goes back to 1981 and the work of Emerson and Clark and Sefakis, was the idea that we can use the state transition graph as a program. We can view the state transition graph as a program as a model for temporal logic. Our model for temporal logic is just a directed graph in which vertices in the graph correspond to system states and edges correspond to the execution of program instructions. And then we can write down our correctness properties, the correctness properties that we're interested in testing for our system, as a formula phi of temporal logic, and we just have to check whether that formula is true in the model corresponding to the state transition graph. And this is the notation that we use to describe this. This is why it's called a model checking problem. We're checking whether the formula phi is true in that model. And the point is that process can be reasonably efficiently automated in many cases of interest. It's a very successful technique, very widely used. There are very many model checkers now available. The best known of those are Spin and SMV, Prism by my colleague Martin Kwiatkowski here in Oxford, and many, many others. And the language that we're going to focus on mainly in this talk is a language, for the language for writing down those properties phi that we're going to use in this talk is the language of linear temporal logic, which is a very, very commonly used language in this framework. So here is a picture of this. We've got our state transition graph of our program on the top left. We've got our property. This is a temporal logic property. Don't worry about what it means. We're interested in asking whether the system on the left satisfies this property on the right. Think of that property on the right as being a query. And what a typical model checker like Spin or SMV will do is they will automate the process of checking whether that property holds of this model, and they will simply say, yes, it's true, or no, it is not true. And useful model checkers, if it's not true, will give you a counterexample. Let's have a quick look at the language of linear temporal logic. Basically, it's classical propositional logic extended by some strange looking what are called temporal operators. And these are operators for talking about state sequences. And so the operators that we have here, the circle operator means in the next state, the diamond operator means eventually, the box operator means always, and the U, the binary U operator means until. So here are some example formulas. Eventually not pandemic means eventually there will be a state on which we're no longer in a pandemic. That's just a temporal logic property, which of course we all fervently hope is true. A typical property that you might want to write for a computer program is something like always not crash, where crash is a particular proposition which represents a bad state of the program. So we want to check that our program never crashes. That's a formula that we might write to do that, slightly simplified formula. We can combine these two operators. So this says always eventually drink beer. It says no matter how far into the future we go, there will always be a subsequent point at which we drink beer. So we will drink beer infinitely often. Hooray. A sadder example of a temporal logic formula is eventually always dead. What that means is eventually we will reach a point after which we are always dead. A much sadder example than drinking beer infinitely often. And then finally, an example of one of the binary operators, not friends until apologize you. So we are not friends until you apologize. What that means is there's a future point at which you apologize, and all the points until then we are not friends. Okay, so let's introduce the idea of rational verification then. It's like model checking, but a little bit different. And it's a little bit different because we adopt a game theoretic standpoint. Now, what model checking will do is it will typically try to find whether there is some execution path in your program, some way of executing your program that would make that temporal logic formula true. The problem is not all of those paths would happen if the agents in the system, which think of those as being like the traders in the flash crash scenario that are buying and selling stocks and shares and currencies and so on, some of those paths won't happen if those agents act rationally. So what we want to do in our framework in rational verification is check the properties of the paths that could arise through rational action, that could arise by these agents acting rationally. And what does it mean to act rationally? The particular viewpoint is that we adopt the viewpoint of game theory. And game theory, deriving from economics, provides us with a number of what are called solution concepts, which attempt to characterize rational behavior in multi-agent systems. And the key solution concept that we use is called Nash Equilibrium, and I'll come back and explain a little bit more about Nash Equilibrium in a moment. But basically think of Nash Equilibrium as being a description of rational behaviors by agents. And the two key concepts that we consider are E-Nash and A-Nash, Nash reachability and Nash invariance. And what E-Nash says is, given a particular temporal property, is there some rational sequence of choices by the agents on the system which would result in that temporal property holding? The A-Nash says, would that temporal property hold no matter what the rational choices were? That is, this temporal property will hold irrespective of how the agents act as long as they act rationally. So this is now the replacement for our picture. We've still got our model on the top left there. This is the replacement of the picture of model checking. We've got our model in the top left, where the states correspond to, the vertices in the graph correspond to system states and the edges to transitions. We've got the player preferences now. We need to know what the preferences of each of the individual agents are in order to be able to judge whether they're acting rationally. And we've still got our query, the query that we're asking about system behavior. So think of those preferences in the flash crash scenarios. They're trying to make money. They prefer more money to less money. And what our rational model checker will do now is it will say, yes, this claim is true on some Nash equilibrium, or no, it's not true on any Nash equilibrium. So it could happen through rational action, or it couldn't happen through rational action. The particular framework that we've developed to instantiate this idea is called Reactive Modules Games, and it's based on a high-level modeling language called Reactive Modules, which was developed in 1999 by Rajiv Allur and Tom Hensinger. So this is an example. It's a guarded command language. I'm not going to give you the details. You write guarded commands for initialization. You write guarded commands for updates of an agent. These agents are called modules in the Reactive Modules framework, and each agent, each module, controls a bunch of variables. So I say these initialization guarded commands, which are used when the agent starts running, just define how the agent starts running, how it initializes its variables initially, and then the update rules say how it will update those rules subsequently. So the formal definition of a reactive modules arena is we've got a set of agents where each of those agencies is just exactly one of those modules that we saw on the previous slide. We've got a set of Boolean variables. These are the variables that these agents are controlling by assigning values to them. And then for each agent, we've got a module which says the variables that agent controls, its initialization rules, and its update rules. And the initialization rules and update rules are exactly in that form that we've just described. Okay, so that's a reactive module game. How do we model strategies? Basically, then the game is played over an infinite number of rounds where initially a module uses its initialization rules to choose how to set its values, and then subsequently it uses its update rules. The technicality here is that to model such a strategy, which just defines how it chooses which of its rules to apply, we use finite state machines with output, technically Moore machines. Details aren't that relevant. It's just essentially we're using a computer program to decide how to choose those rules to update. A strategy profile is a collection of strategies, of a finite state machine strategies, one for each of these agents. And when we've got one strategy for each of these agents, which is telling it how to choose which of its rules to apply, then we've got what we call a strategy profile. And each strategy profile induces a unique computation, a unique run in the system. So this is just an infinite run where agents are making choices according to their strategies. Okay, finally, we need the notion of Nash Equilibrium, and the notion of Nash Equilibrium is very simple. Here's the formal definitions on the slide. If you're watching the video later, you can pause the slide and read it, but the basic idea of a Nash Equilibrium is a collection of strategies is a Nash Equilibrium if nobody regrets their choice of strategies. Nobody could have done better by choosing some other strategy. What I didn't tell you is how we model preferences. So how do we model preferences? The way that we do it is we assume each player has a temporal logic goal, and they're over here on the right. They're written down as gamma 1 and gamma 2. These temporal logic goals just describe for each agent how that agent wants the system to be. It just describes how that agent wants the system to be. Okay, so this is our framework for rational verification then. What we want is a program which will take a description of a system, it will take our player preferences, think of that as want to maximize money, and then it will take a query and it will tell us whether that query is true on some Nash equilibrium of the system or no, it doesn't hold on any Nash equilibrium of the system. A bit more technically, some decision problems and their complexity in this case. The membership problem, we're given a reactive modules games and we're given a strategy profile, and we're simply asked, is that strategy profile a Nash equilibrium? Turns out that problem is p-space complete. The interesting thing about that is it's no harder than the model checking problem for LTL that we talked about earlier. The non-emptiness problem, we simply ask whether a reactive module game has any Nash equilibrium. It's not the case that there is guaranteed to be one. This problem turns out to be much harder. It's 2x time complete. And where that completeness comes from, that complexity where it comes from, is from the fact that this problem subsumes a problem called LTL synthesis. But then we come to our two most important problems, the E-Nash and the A-Nash. And just to recap, in an E-Nash problem, we're given a reactive modules games, and we're given a temporal logic formula, our query, and we want to know whether that property, that query, holds on some path that could be generated by a Nash equilibrium collection of choices. In the A-Nash problem, we want to know whether it holds on all paths that could be generated by Nash equilibrium computations. And it turns out that the E-Nash and the A-Nash problems are both 2x time complete. Because of this high complexity, you need fairly sophisticated algorithmics in order to be able to do anything. And you can guess the punchline. We've developed those algorithmics, and there's a system. You can follow the link there, eve.cs.ox.ac.uk. You can play with this system. You can write down some systems and some temporal logic goals and experiment to find out what the equilibrium properties of these systems are. So what it does is it takes as input an arena specified in reactive modules. It takes goals for each player specified as linear temporal logic formulas, and it will solve the E-Nash and A-Nash, and in fact also the membership problems. And under the hood, there are a lot of translations going on from various different kinds of infinite automata to other infinite kinds of automata. And for those that are in the know, we make heavy use of what are called parity games, which is an important class of games that are they're important in an important class of games in computer science. Okay, I don't have much time in this talk, so I have to wrap up. So I love rational verification. It raises tons of interesting scientific and technical challenges, which I've only really skimmed over in this talk. And in terms of applicability, it's really limited to rather small systems. So in future work, and I'm very proud to be the recipient of one of the Turing AI World Leading Researcher Fellowships from UKRI, what we're going to try and do is we're going to focus on trying to scale this approach to large systems by marrying these ideas to an approach called agent-based modeling. And agent-based modeling focuses on doing simulations of multi-agent systems, Monte Carlo simulations of multi-agent systems. So what we would really love to be able to do is to build those Monte Carlo those agent-based models, perhaps for epidemiological modeling, like pandemic modeling, and be able to query them in the way that I've sketched here. So I've run out of time. Thank you for your attention. And thank you again for giving me the Lovelace Medal. I'm tremendously proud.
Okay, thank you very much indeed. So I believe you all thoroughly enjoyed the talk, and you will probably have some questions for Mike and Nick. I can see there's 2 in the Q&A already. Please go ahead and type more in. We'll see how many we can get in. First of all, again from Bashan Sebe, congratulations to both of you. Inspired by your work when I was a PhD student in the late 1980s. Given the national security interest of at least one of you, I wonder if and how irrationality, perhaps motivated by or as a consequence of malice, affects how multi-agent systems can or should be modeled, used, or indeed attacked.
I might have a go at that, since I think I'm the one you're talking about, Tony. I think when you build multi-agent systems, you naturally, unless it's all within one organization, you naturally end up thinking about self-interest, and which naturally leads to sort of how can people or other agents circumvent the system, because it's intrinsic. As designers of multi-agents, open multi-agent systems, we will assume that if agents can get some benefit from being mischievous or not telling the truth or any of those sorts of things, then that is our default design assumption. So sort of in this work, it kind of is what you think about, and the aim of the analysis and some of the tools that Mike was speaking about and that we used in ORCID are very much to help protect against those sorts of things. So we absolutely don't assume rationality, but we do often assume self-interest. Mike,
so
I don't know if you want to add to that.
Yeah, I think it's a very good question for our setting. So the work that I described in my talk assumes perfect economic rationality, sort of Nash equilibrium, everybody's optimizing basically against each other. And there are all sorts of assumptions built into those models, like, for example, very often the assumption that everybody knows everybody else's preferences and possible actions and so on. Which is one of the reasons why those models don't scale to terribly well to very large systems. So this is why we're looking at alternative approaches using agent-based modeling. And in the agent-based modeling approach, we don't assume rationality whatsoever. So the project that I've got that's just started, that UKRI project that I mentioned, we're going to be looking at various different ways of obtaining realistic agent behaviors. For example, using you guessed it, machine learning to try to learn agent behaviors. I mean, one of the ideas is looking at, for example, in epidemiological modeling, which we're not actually doing, although everybody keeps asking as if we are. But I mean, one of the things that you might do is look at social media, Twitter feeds, to look to see, to do sentiment analysis on Twitter feeds to get some understanding of, for example, whether people are wearing masks or whether they're, how they feel about the vaccines and so on. And so we're using a range of different ways to generate plausible, realistic agent behaviors. And in the economics literature, the area is called behavioral game theory that studies those. I mean, it's very well documented that there are limitations of assuming sort of perfect rationality models. But it's a very sensible question and one we're very, very mindful of.
Thank you. Claudia Eberlein says, great talks. Naive question from a physicist. Could one agent outdo another by acting more intelligently, not just act faster?
Yes, is the really short answer to that, Claudia. So in a lot of the work that I've been interested in automated negotiation, for example. And if you have a better negotiation algorithm, however you construct it, however you come to that case, then your agent is likely to do better than a less good agent or a less effective agent, and therefore it's likely to end up with a better outcome. So it's not all about speed. I mean, some of the things that Mike spoke about, the financial trading is largely about speed, sort of the high volume, high frequency trading. Speed is the essence of it. But in many other encounters, in many other of these things, it's the smartness of the strategy.
Yeah, and I would just come in and say, one of the interesting things about working in this area is you can design, for example, negotiation protocols that have certain provable properties. And I'm dumbing down the explanation of those, but I mean, intuitively, what you can do is you can design these protocols so that you can get mathematical guarantees about how your agent is going to be able to perform. Or to put it another way, you can prove that your agent can't be ripped off if it uses this protocol. That's something of a dream. We're not there yet, but that's the kind of thing that people have studied. In fact, Sarit, who's going to give our vote of thanks, I think, in a moment, is one of the world leaders in that particular area.
Okay, thanks. We've got two more questions for the same person. I'm just going to take one of those in the interest of time. So this is Vahidi Yazdanapa. For Nick, long before recent discussions around responsibility in AI, you argued for the relevance of collective responsibility reasoning in AI systems. What was the motivation back then in the 90s? It would be great if you could share early discussions around adopting the joint intention / responsibility view for engineering multi-agent systems.
So sort of inspired by several others, including Sarit in this area, I wanted to be able to try and formalize what it meant to do something as in a team. And for me, sort of that means more than even everyone just doing their bit. So sort of, you could achieve a joint goal, a joint team, if everyone did their bit. And that's sort of a part of it. But actually for me, the responsibility and sort of being a team member meant that actually you would actively support other agents in your team with their piece or their piece of the action over and above just doing your own. So being in a team meant something more than everyone just doing what they'd been allocated. And that's the bit that I wanted to be able to capture with the responsibility. There were, as I said, other models, shared plans that Sarit was very much involved with, in the STEAM framework from Milintombe at the time. But that's the essence of what I was trying to get at in that work.
Thanks. I said that was the last question, but I'm just going to take one more because I think this could be interesting, from Jane Lisa Waite. When should we introduce the idea of multi-agents to students in school? Often we focus on algorithms for single agent computers. Should we be introducing ML cooperative agents earlier?
I think it's a much more general question than agents and multi-agent systems. I mean, I think part of what we should be doing in school is not necessarily, I mean, I don't think it's necessarily so important to teach students, fundamental AI algorithms like A* or gradient descent or something like that. But I think if I could teach students one thing, I think it would be a healthy disrespect for AI. I think readiness to question it, not to be dazzled by what by the grand claims that companies are so willing to make about AI, and it's not to trust it, but to have a healthy degree of skepticism. I think, and to understand the limitations of what AI is. I mean, I think we're still, we're undergoing this incredible transition in society that started with microprocessors in the 1980s and then went through the internet in 2000 and then the smartphone revolution. And each of those has really fundamentally changed society. And I think, we're scrambling to keep up with that in terms of what we teach to our children. But from the point of view of AI, I think understanding its limitations, what it can do, what it can't do, and being ready to question it, I think is just particularly important. Of course, if schools want to hand out my textbook to all their kids, that's also fine.
Thank you, Mike. Thank you, Nick. I see two more questions there, but we're over time already. Maybe whilst we're taking the vote of thanks in a moment, if you have time, Mike and Nick, you could try to type the answer to those two questions if you feel so motivated and able to do so. But whilst you're doing that, I'd like to invite, thanks to Mike and Nick for their talks and for their answer to the questions, and I'd like to invite Professor Sarit Kraus from Bar-Ilan University in Israel to give the vote of thanks to our speakers tonight. Thank you, Sarit.
Hello, I'm very honored to present the vote of thanks to my friends Mike Waldridge and Nick Jennings. I'm sorry we can't meet in person, and I'm sending my congratulations from Israel and thank them for their excellent talks. Nick and Mike are leaders of the multi-agent system research community, both intellectually and organizationally. In the first part of their talk, their joint part, they describe their foundational research in the early days of the multi-agent system research. And Mike mentioned their 1995 joint paper entitled Intelligent Agent Theory and Practice, which has had enormous influence on the development of multi-agent system as a whole. This article articulated a vision of what the main goals of the field should be, what the main research challenges are, and defined many of the fundamental concepts that underpin the field. The vision articulated in this article has been incredibly influential, as evidenced by the article's astonishing citation record. Since it was written, it has had 10,860 citations on Google Scholar. Well, this was yesterday. I assume if I will check today, they are even more. This is the most cited article in the entire field of multi-agent systems. And it's important, as Mike Lack said at the beginning, was recognized by the IFMAS, which awarded it the 2008 Influential Paper Award. From the organization aspect, Mike and Nick play an important role in launching the lead and leading all the important institutions that are required for the successful research community. Without them, I'm telling you, there would not be a multi-agent system community. For example, to name a few, Nick was the first editor of the Journal of Autonomous Agent and Multi-Agent Systems, and Mike replaced him at the end of his term and went on to lead it for additional 7 years. Together, they were the founders of the ATL workshop, and that eventually was merged into the AMAS, our joint main conference of the multi-agent system community. Mike was also the first elected president of the organization. And well, an additional thing, I can't count everything, but in 2001, he published a textbook titled An Introduction to Multi-Agent Systems. And guess what? This is the best intro book to multi-agent system, even until today. And personally, I remember how in the 90s, I was amazed how these young researchers, you saw their pictures, were able to do such great research while contributing so much time and effort and idea and innovation to the formation of the community. Going back to the exceptional research, Mike and Nick's research complement one another. Nick comes from the practice to theory, and Mike comes from the theory to practice. Even if I had a few weeks, I could not describe all the research contribution. From my personal view, I have, I think, more than 20 joint papers with Mike and more than 7 with Nick, and I'm only one of the collaborators. So if I will summarize the work, Nick had made tremendous contribution to algorithmic aspect of multi-agent system. For example, to one of my preferred topics, automated negotiations algorithms. Most importantly, he made multi-agent system work real. He was the lead system architect for one of the world's first industrial deployment of multi-agent technology in the area of electricity, and has substantially been involved with deployment of agent-based solutions in many domains with a range of companies and charities, and the ones that he mentioned in his talk, the Disaster Response Charity Rescue Global that we heard about. Mike has made huge contribution to the theory of multi-agent system. In his talk, he focused on verifying equilibrium of multi-agent systems. And I must tell you, if we will not be able to verify multi-agent systems following Mike's leadership, no one will use them. So this work opened up new and important research direction. I want also to mention his work on developing and promoting cooperative game theory with his co-authors. Again, another book on computational aspect of cooperative game theory that is a key text in this area. So let me conclude. I cannot think of researchers deserving the Lovelace Lecture medal more than Nick and Mike. Congratulations.
So thanks very much indeed, Sarit, for that great vote of thanks. And indeed, thanks to all the speakers at today's event. I'd also like to thank Pam Fagan, Maxine Leslie and Julie Adamson at the BCS for all their support of this event and the award process. Also thanks to the award committee and the referees who put time into the process. Finally, all that remains for me is to thank you for joining us at this evening, and we hope you enjoyed it. Thank you. See you next time. Bye-bye.